Hi, my name is Naftali Lazarovich and I'm a professor for soil physics and irrigation at Ben-Gurion University of the Negev. I'm also an associate editor in Vedozone Journal. One of the nice features in Vedozone Journal is the Focus Topics. Focus Topics collects recently published content to highlight the important gains in scientific understanding in specific field of Vedozone research. The goal of the Focus Topics is to increase the feasibility of the key scientific concepts of importance to Vedozone Journal readers, thus providing continuity and follow-through on essential research topics. One of the focus topics is soil plant and rhizosphere processes. This focus topic features articles that investigate the rhizosphere as well as plant and soil interaction and the interface between soil physics, biology, hydrology, and ecology. It presents original, fundamental, or applied papers on the impact of soil on plants and vice versa. Featured papers deal with energy, water, and nutrient fluxes in the soil-plant system. Of particular interest are the impact of function and functioning of the rhizosphere, carbon cycling, and solid, gas, and liquid fluxes between plant soil and the atmosphere. It also includes modeling studies that improves the understanding of the soil-plant system functioning and technical articles proposing new ways to monitor or measure the soil-plant system. The interface between root surface and the soil, the rhizosphere, play a critical role in root soil processes. Proper characterization of the rhizosphere, which differs in biological, chemical, and physical properties from the bulk soil, and its implementation in root zone process model is therefore of great importance. Three excellent presentations are offered in this magazine. The study of Landon et al. Evaluate root biopores interactions at the root system scale under different soil physical and environmental conditions using a mechanistic simulation model and also extensive experimental field data. The study of Haber-Pohlmeier et al. Uses a combination of magnetic resonance imaging, MRI, and neutron-computed tomography for investigating soil root system non-invasively. And finally, the study of Bernard et al. Provides a key missing link between pore scale mechanisms and macroscopic alternation of soil hydraulic properties and soil water dynamics induced by mucilage and EPS. I hope that you enjoy these presentations.
Hi, my name is Magdalena. I'm from Forschungszentrum Jülich, and I would like to present to you a recent study about modeling the impact of biopores on root growth and root water uptake that I conducted with my colleagues also from Jülich, as well as from the universities of Kassel, Bonn, and Berlin. So first of all, what are biopores? They are voids in the soil created either by earthworms or decaying plant roots, and they are important because roots can use them to penetrate compact soil layers and to gain access to subsoil water resources. What we wanted to do in this study was to combine extensive experimental field data with a model in order to give explanations for interactions between root growth in biopores and root water uptake, and secondly, to test the impact of biopores on root growth and root water uptake under different soil physical conditions. So the model we used was the RSWIMS model. RSWIMS combines a root growth model with a soil water flow model and a root water uptake model. Combining means that the root growth is influenced by the soil moisture conditions. For the root water uptake, the transpiration demand is set at the root color and depends on the atmospheric conditions. For our study, we additionally had to implement the impact of biopores into RSWIMS. For that, we used a recently developed model that takes into account the impact of biopores on the root growth rate as well as on the root growth direction. And additionally, we implemented the impact of biopores on root water uptake into RSWIMS. So basically what we did was we simulated the growth and water uptake of a single wheat root system in soil with biopores in 3 dimensions over a whole cropping period from April to end of July. We set up different simulation scenarios that take into account the different soil physical conditions. So first of all, since we wanted to evaluate the impact of biopores, we did scenarios with and without biopores. Secondly, for the root water uptake, we took into account limited as well as unlimited root water uptake in biopores. The limited root water uptake means that if a root is located in a biopore, only a part of the root surface is in contact with the biopore wall. Thus, a root will take up less water. In the second case of unlimited root water uptake, we assume that a root that is located in a biopore can take up just as much water as it would if it was located in a bulk soil. Additionally, we took into account 2 scenarios of subsoil bulk density, either low or high. In the graph on the left, you can see the impact of biopores on maximum rooting depth as well as root length density. What you can see is that biopores increase both maximum rooting depth as well as root length density. In general, both maximum rooting depth and root length density were lower in more compact soil, which is clear because of the increased soil penetration resistance, and limited or unlimited root water uptake did not have any influence on maximum rooting depth or root length density. In the graph on the right side, you can see the impact of biopores on the cumulated root water uptake. Now, in the first part of the graph, until mid-June, no stress occurs, thus the potential root water uptake rate is met. Afterwards, there is the stress onset, and transpiration demands can no longer be met. What you can see is that in the scenarios with biopores, higher transpiration occurs, which is, of course, very positive. If we look at that more closely, what we can see is that the impact of biopores on the cumulated root water uptake is greater for dense than for loose soil. Now, this is because also the relative increase in maximum rooting depth as well as root length density was greater for more compact than for loose soil. And secondly, the impact of limited root soil contact in biopores on root water uptake is only small. Now, this is because actually not the root hydraulic conductivity was the limiting factor, but much more the limited soil water availability. Now, these results are interesting in general, but they can also be very useful for larger scale simulations in 1D crop models that can only take into account the impact of biopores on root growth and root water uptake implicitly. So if you're further interested in this study, I would invite you to read the paper. And anyway, thanks a lot for watching.
Hello, I'm Sabina from the former group of Professor Blümich at the University in Aachen, Germany. I'm pleased to have the opportunity to introduce you to our paper in the field of rhizosphere research, on which I worked with my colleagues from the University in Potsdam and at the Research Center Jülich. So our paper focuses on 3-dimensional rhizosphere imaging in order to obtain a more detailed analysis about rhizosphere functioning. Well, rhizosphere research is challenging since the root soil interface is essentially a soil compartment and therefore opaque. And furthermore, it is small in size. That means that we need non-invasive, high-resolution 3D imaging techniques like MRI and NCT or X-ray CT. While X-ray CT and NCT are extremely valuable tools to probe the solid matrix and the absolute hydrogen atom density, key information about transport quantities and dynamical properties are not directly accessible. So that means a combination of MRI and NCT would make it possible to measure the hydrogen atom density, which corresponds to the water content, and simultaneously access relaxation times on the same sample. But a method combination requires a co-registration of 3D images because different field of view, resolution, and orientations need to be matched mutually in 3D. An example is given in this video, which shows the overlay of the images after co-registration. And it demonstrates that the root structure matches almost perfectly, emphasizing the precision in the alignment of the complementary 3D dataset. So the co-registration is a prerequisite for the detailed discussion of our rhizosphere results. In this introduction, I will focus on the profiles of one lateral root in one selected slice measured at high water content. The profiles show a symmetric shape with the root in the center characterized by a high water content. On both sides of the roots is the rhizosphere with an extension in the range of 1 millimeter. The LCT images unambiguously show an increasing water content towards the roots. And from the MRI images, we get the information about the relaxation times. And we see that the relaxation times accelerates if we go from the bulk soil to the root surface. And in addition, this zone of short relaxation times correlates with the water content gradient. So these results interpreted together shows that the rhizosphere has modified properties by an additional gel phase. So now what happens if we look to the profiles after a drying and rewetting scenario? The water content decreases in the rhizosphere, and this decreased water content correlates with the short relaxation time showed before. In addition to that, the MRI images confirm the persistence of this dry zone over a time period in total of 12 hours. So that means that under the conditions of drying and rewetting, we have a change in the rhizosphere properties from hydrophilic to hydrophobic. With that, I would like to thank you for watching this video, and I wish you a great day.
Hello, my name is Pascal Benat, and today I want to share some of our work with you, which was on mucilage and EPS, and how these highly polymeric blends alter the physical properties of the soil solution, and how their interaction with the soil pore space affects the physical properties of the soil. Now here you can see an example of a hydrated blob of mucilage at the tip of a crown root of a maize plant. Now, if the polymer content in EPS or mucilage is high enough, these polymers eventually form an interconnected network. You can see an example here from chia seed mucilage. Now, the physical properties of the soil solution are altered, and you can see in these three graphs one example of maize mucilage. And when soil dries, or mucilage is concentrated, the surface tension at the gas-liquid interface decreases. At the same time, which you see here in the central graph, the viscosity increases and the water potential of the liquid phase decreases. Now, the decrease in water potential represents the force with which water is attracted to this polymer network. So the higher the concentration of the mucilage or the denser this polymer network, the stronger water is attracted to this network. So mucilage and also EPS can decrease the surface tension, increase the viscosity, and they can retain water. Now, introducing mucilage into the pore space and drying such porous media as you see them here leads to the creation of these distinct structures. Now, for a low mucilage content on the top left, you can see the creation of such a filament between two quartz grains. On the bottom left, for a bit higher mucilage content, you see such a pendular bridge, which is a hollow cylinder created between two glass beads. And on the bottom right, for a high mucilage content, you can see the creation of such two-dimensional surfaces which reach across multiple pores in these glass beads, which are represented as, which are blue in this segmented X-ray tomography. So you can see that these two-dimensional structures, the mucilage kept the liquid phase connected even until the soil was very dry. So how can we explain these shapes? So here's our concept. So for low mucilage content, we end up creating these filaments between particles, which their integrity can be explained by the Ohnesorge number. So the Ohnesorge number relates the force of viscosity over inertia and surface tension on the shape of such a liquid bridge. So when the Ohnesorge number is much larger than 1, or viscosity is dominating over the other forces, such a bridge remains intact. Now, for the creation of the other liquid bridges, we need a bit more than the Ohnesorge number. So when the liquid phase is retreating towards the interparticle space and the polymer network is retreating with the liquid phase, eventually a critical viscosity is reached at which the friction between the polymer network and the solid surfaces is too high for the polymer network to retreat with the liquid. Now, at that point, we start to create these either pendular bridges or these two-dimensional surfaces. Now, these pendular bridges are then either drained by cavitation or air invasion. Now, if the polymer network gets stuck at a higher water content, we end up creating these two-dimensional surfaces reaching across multiple pores. So we end up increasing the liquid connectivity. Now, what are possible implications of such an increase in liquid connectivity? Here you see it on the example of hydraulic conductivity. So in a dry soil, eventually, the mucilage amended soil has a higher hydraulic conductivity when dry. Now, on the bottom left, you can see the impact on soil drying. So these two-dimensional surfaces, which might be created in a dry layer on top of the soil, can decelerate the drying of the underlying wet material. And there are more impacts like on soil wettability, which is given in another article of ours, or on an increase of diffusion rate. So increasing the liquid connectivity can also help for nutrients to diffuse through dry soil. If you want to know more about the topic, you can have a look at one of these references. And with this, I want to thank you for your attention.